All right, so we're gonna pick up here, and we've done like we finished out, I think, with number 4. Done a bunch of these, so um, can't remember because I was doing the same handout with the first section. So let's make sure we all on the same page. So can somebody let me know, like, is this where we stopped right on that Friday before spring break? This the last question that we did? I think so, because I know we didn't have recitation that Thursday before. So all right, so we've covered like multiple topics, mainly dealing with moles and being able to convert between moles and molar mass and molarity as it relates to moles too. So a lot of these questions we're working on these were all percent composition leading up to this, but we talked about, I don't know if we did this question right here, but we can do this one first. This is just as a warm up. It says a 55-kilogram woman has 7.5 times 10 to the minus 3 moles of hemoglobin. Doesn't her mass doesn't matter, because what the question is asking is how many hemoglobin molecules is this? Let me get my pen right. And so you see where it says how many hemoglobin molecules is this? And then the second part of the question is what's the quantity in grams? Right. So what do we need in order to find molecules as well as grams if we're given a specific number of moles of a compound? So we have 7.5 times 10 to the minus 3 moles, and we're given the molar mass as well. We're given 64,456 grams per mole. So what do we need in order to find molecules?
Is it the atomic mass?
Well, we have that. We have the molar mass, atomic mass. But if I want to find out how many molecules are in a mole, I have a number I can use, right? I have this number. I got Avogadro's number, right? Which is 6.022 times 10 to the 23rd, whatever per mole. I can put any number in the top, right? And get the number of units or discrete particles per mole, right? So let's do that. So we're going to find out molecules first. And that's going to be 7.5 times 10 to the minus 3 moles. We're going to just multiply that by Avogadro's number, but for the discrete unit that we're looking for, we're going to put molecules in the top. So it'll be 6.022 times 10 to the 23rd. Sorry about that. Molecules per mole. All right, so the moles are going to cancel and we'll end up with molecules. And this is and this is just another way to manipulate moles and determine discrete particles, molecules, atoms per mole, molecules per mole. Doesn't matter what we put in the top. All right. Can somebody calculate that real quick? It'll be Avogadro's number, which is 6.022 times 10 to the 23rd. And then we're going to multiply that by 7.75 times 10 to the minus 3. Somebody tell me what you got for that. So anytime we want to find out discrete particles per mole, we can just use Avogadro's number. Right? We can put any number in the top. It doesn't matter what it is. We can put that number here. I'm gonna write that in here. Not with a highlighter. I'm sorry. Anybody got the number yet?
I got 4.5165 times I'm sorry, times 10 to the 21.
So 4.5 times 10 to the 21st.
Yes.
Okay, we'll take that. And that's molecules, right?
Yes, sir.
All right. So 4.5 times 10 to the 21st power molecules in 7.5 times 10 to the minus 3 moles. All right. And that just shows you really the relationship too between moles and that's a lot of molecules. And that's a very small number of moles. Right. So, and that's something to think about, especially when you're doing chemistry and when you're thinking about like specifically doing a particular reaction and how many moles we start with. But when we think about like something that's 1 mole, that's really 6.02 times 10 to the 23rd molecules for every 1 mole. So there are a lot of particles, housed within 1 mole of a substance. So just something to think about. All right, how are we going to get the grams? That's the other part. What's this quantity in grams? How are we going to get that? Do we have everything we need to get grams from moles? What do we need to get grams from moles? Don't we need grams equals what? Moles times what? Molar mass. We can always manipulate that. Uh-oh, didn't try to do that. We can always manipulate that. So moles times molar mass will give me grams. So I have the moles, right, already. So this is what, 7.5 times 10 to the minus 3 moles. And then that's going to be times 64,456 grams per mole. So the moles are going to cancel. What do we get from that? Excuse me. So 7.5 times 10 to the minus 3 moles times 64,456 grams per mole. That's a heavy molecule, but it also contains like iron as well. So that contributes to its molecular weight.
I got 483.42.
So you said 483.46.
42.
Okay, let's just say 483 grams. So that's about a pound. That's roughly that's a little bit over a pound actually. Because 1 pound of 1 pound is equivalent to 454 grams. So that's a little bit over. That's a lot of hemoglobin. But she weighs 55 kilograms. So that is about 55 times 1.6 is that. She weighs a little bit over 100 pounds. So, or close to 100 pounds. She's little, tiny. And 1/10 of her mass is just about 1/10 of her mass is hemoglobin. Wow. Didn't think about that when we were solving this with the other section, but that's pretty interesting. All right, any questions about that? All right, let's go to number 6. Number 6 asks, what information is needed? I said 1.6. I'm thinking about kilometers and miles. My bad. So 55 kilograms is the same as 5,500 grams, and then that's times 454 or divided by 454. So she is roughly, she's a little bit over 100 pounds. But that the conversion I said earlier was not right. That was kilometers and miles, 1.61. Anyway, let's go to the next one. What information is needed to determine the molecular formula of a compound from the empirical formula? So if you have the empirical formula and you want the molecular formula, how do you calculate that? What's the process for doing that? What do we have to do first? Right? Don't we need formula units? Is that right? And that
Yes,
is,
sir.
and that is, how do we determine formula units? Is it it's the molecular formula divided by the empirical formula? Is that right? The mass, right? We need the molar mass of the molecular formula, and then we need going to divide that by the molar mass of the empirical formula. And that's going to give me N. And then if I take the N and then multiply it times the empirical formula and distribute it, right? Then that'll give me the molecular formula. I know this is kind of rusty because this was like a week before spring break when we did this, but so in order to find the molecular formula from the empirical formula, first you use the empirical formula to find formula units. And then you can take the formula units and distribute them through the empirical formula to get the molecular formula. All right, let's do number 7. Any questions about that one? All right, let's do number 7. Number 7 is just like what we did up here. It's a percent composition problem. So number 7 as, let me see, yeah, we get to molarity next. We got plenty of time. Number 7 as determine the percent ammonia All right, it says determine the percent ammonia. So this is what we're looking for in this cobalt complex to 3 sig figs. All right. So what do we need to do? This is just like one of the problems we were working right before we left for the break. What information do we need in order to find the percent composition of this compound? Because that's what we're basically looking for, right? We're looking for the percentages of each one. And then we're going to take those percentages and they all have to add up to 100. So we need to find out how much each one of the atoms in this compound contributes to that, to the overall molar mass of the compound. So that's how we solve this problem. So we solve it by first, sorry, poem hit the screen. All right, first we got to find the molecular weight of the compound, and then we're going to find the individual percentages. Right, so the molecular weight is going to be, we got cobalt. It asks for ammonia, so we're going to leave that intact because we know we can figure out how much one molecule of ammonia, what the molar mass is of that. So we're going to leave that intact. And then we have actually 6 ammonias. And then we have 3 chlorines. Right, and so we're going to take this and multiply it. So the 1 multiplied by the molar atomic mass of ammonia, which is 58. 0.93 grams per mole. And then for, did I say ammonia? I'm tripping. Cobalt. The atomic mass of ammonia is going to be 17 grams per mole. Because if we take the 3 hydrogens, which each have a mass of 1 roughly, and then the nitrogen has a mass of 14. So since it asks for ammonia, the whole molecule, we're gonna just leave it intact and say it's that the mass of it is 17 grams per mole. And then the chlorines, we're gonna take that, so that'll be times 35.35 grams per mole. Right, so what's my total here? My total molecular weight for that cobalt complex.
What is the last number?
Oh, I'm sorry, it's 35.35.
Okay.
$35.35.
I got 111.28.
For the ammonia. I mean, I'm sorry, for the chlorine.
Oh wait, no, I'm sorry. That was the total for like all of them. That's my bad.
So you said 111. So let's see. So we got 6 of these now. This is gonna be over 100 by itself because 35.35 times.
My bad. Yeah, no, I see. I did that wrong. That's my bad. I see it now. I got
Okay.
you.
All right, cool. We good. We good.
For chlorine, I got 106.05.
106.05. All right, we'll take that. 06.05. And this is grams per mole. And then what about cobalt is going to stay the same, right? That's going to be 58.93 grams per mole. And then what about the ammonia? 17 times 6.
That's 102.
102, good. So now we just need to sum all these up, right? So if we sum them up,
Yes, sir.
what do we get if we sum them all up?
I got 267.
On the head?
I rounded up. It was 266.98.
Yeah, let's take that one. Let's take that 266.98. That's more precise. Even though it's only 0.02 difference, it's a little bit more precise. So we'll leave it right there. All right, so let's take that. Now, how are we going to figure out the percentages of each one? What do we need to do? See, this is the kind of redundancy of these types of problems, because we just went through and found out the individual like molar masses for each atom that's involved. But to find the percentages, all you have to do is take the part over the whole. That's what percent composition is. Right, so the parts for cobalt, we can just say 58.93. Sorry about that, 9. I'm getting used to this new stylus. I should have brought the anti-palm glove too at the same time, but I didn't. I ordered it though. So that's divided by 266.98. And then the whole thing times 100. All right. And then if we want the ammonia, we can just take what 102, which is what the ammonia contributes to the overall molar mass. Right. This is the part over the whole, 266.98 grams per mole times 100. And then for the chlorine, it'll be the same thing, 106.05. And this is NH3. That's CO, and that's Cl. So 106.05 divided by 266.98. And all the units for both are grams per mole. All right, what we got for cobalt?
I got
22.072.
22.07.
Sorry.
That's okay. That's good. I like that. 22.07% for cobalt. All right, good. What about ammonia? Because that's the one we're asking about anyway. We went from over talking to nobody talking. Nobody
I
talking.
got 38.
38% on the head, or is it a decimal?
Yeah, on the head.
And then so chlorine will have it by default. It's got to make up the difference to get to 100%, right? So what do we have for chlorine? Should be somewhere close to 40%.
I got 39.72%.
39.72.
Yes, sir.
All right, we'll take it. And I know with some of the rounding and the decimals, it may not necessarily be right at 100, but it's close enough to 100 that you know, all right, this is legit. You know, sometimes that's why sometimes you don't want to round until you get to the end, because that way you keep your precision and your accuracy with your calculations. All right, good. Any questions about that? So this is again a percent composition problem, and this is dealing with the skills involved with this problem are how to determine molecular weight, and then how to go back and find the part over the whole. You can do this for any molecule. If you know the formula, you can figure out the molecular weight. And if you know the formula, you can go back and figure out the part over the whole, right? That's the skill set that we're developing with these types of problems. All right, let's go to number 8. Let's have questions about number 7. All right, let's go to number 8. And number 8 is we're shifting gears now, dealing with molarity, right? And I think we did some molarity questions in class. So again, let me just give the definition. Just want to zoom in on that. Molarity is based on moles of solute. You can divide that by liters of solution. All right. And so knowing that, right, this is basically moles per unit volume. That in order to find the molarity, which is also known as the concentration, these units are absolutely necessary. You have to have your top number in moles, and your bottom number, the volume, has to be in liters. That's required, and then the volume. Why am I saying that? Because in some of the problems, you might not get liters for volume. You might get milliliters. You might not get moles initially, but you may get grams, right? And so knowing that we have to have the top unit, top number in moles and the bottom unit in liters. If you get anything else in the problem, you're going to have to do some manipulation of the information to get what you need, right? So for this one, let's start out with A. Here it gives us, and we're going to determine, excuse me, the concentration. So it gives us the number of moles, and it gives us a volume in liters. So we don't need to do any manipulation of that. We can take that as is, put those two numbers over each other, and then you'll see big M, which is molarity, is 0.444 moles divided by 0.654 liters. And then when you express this as the answer, you just leave it as M. Sometimes you'll hear it referred to as molar, or and that means the same thing. It's just molarity. What do we have for that? 0.444 moles divided by 0.654 liters.
Got 0.67889.
So we'll say 679 molar. So when you see that big M like that as your unit, you just say molar. So if I ask you what the concentration of that solution is, you'll say 0.679 molar. It's a 0.679 molar solution. All right. So having said that, let's look at B. What do we need to do for B? We have our volume. That's already in liters. But the phosphoric acid that's helping to make up the solution, because the way you make a solution is to take that phosphoric acid and then dilute it up to that volume using a volumetric flask. We got 98 grams of phosphoric acid. Is that okay? Based on our units?
We need to convert it to moles.
Gotta convert it to moles. You start out with grams, you cannot stay there. You can't do grams over liters, because that's not gonna give you molarity, it's gonna give you a density. And then even with that, you're gonna have to turn the liters into milliliters. So with this, if you're looking for molarity, the top number must be in moles. So how do I get, we're gonna convert this to moles. How do I get moles from grams? Now this is a ubiquitous calculation. You cannot forget this calculation. You might forget a lot of other stuff, but you cannot forget how to go from grams to moles ever. You're gonna need that calculation for the rest of your STEM career. If you plan on sticking around in STEM, you're gonna need to know how to do that without thinking about it. So how do we get from grams to moles?
You divide by molar.
Divide by the molar mass. So grams pen over molar mass. The moles. That's the first thing we learned all the way back when we first started studying this chapter. So we're going to take that 98 grams divided by the molar mass of phosphoric acid, which we don't know. We could Google it, but what if we don't have Google, but we have a periodic table? Can we calculate it?
Yes, sir.
We can calculate it. We got 3 hydrogens. So this is going to be 3 times 1.00. I need to thin this pen out a little bit. Hold up. 3 times 1.008. And then we got 1 phosphorus, which I think is 30 something. Am I right? 31, somewhere around there. Anybody got phosphorus off our periodic table? Isn't it 30.94 roughly?
Yes, sir. It's 30.97.
All right, 30.97. All right, so 30. So this will be 1 times 30.97 grams per mole. All right, so we got everything we need. We just need to add those numbers up, do that quick calculation and add them up. Right. And if you're ever in a bind, you don't have a calculator, you can always round the numbers on the periodic table, the atomic mass, and just round them to the nearest number. So that's going to be 3 plus 31 plus for oxygen will be 16. So plus 64. 64 plus 3 plus 31. What do we get? So 64 plus 3 is 67 plus 31. It's going to be 90, somewhere around 98 grams per mole. Not written in a
I
hollow.
got 97.95.
So 98. Okay, good. We're going to keep that more precise number. You said 97.95
Yes, sir.
grams per mole. So the grams are going to cancel. I'm going to be left with moles. You can see that that's going to be roughly 1 mole. Is that right? Top number is 98. Bottom number is basically the same as top number. What do we got? 0.99999 moles, something like that. Or 1.0000 something moles. Is that right?
Yes, sir. You get 1.000.
All right, so we're just gonna say 1.00 moles. All right. So now we're good. We got our moles. We know our volume, which is 1 liter. This is this is all academic. So now we're just finding M, which is going to be 1 mole. And then I know this is stupid, but it's not the numbers that matter. It's the setup and the repetition, learning like how to convert, doing the conversions over and over again until it's second nature to you. So this will be 1.00 moles divided by 1.00 liters. And the concentration is 1, right? 1 molar. So we'll say that this is 1.00 molar phosphoric acid. It's pretty concentrated, to be honest with you. It's enough to if you get it on your skin, you're going to feel it and know it. All right. So all of these problems are identical. You're either going to have to convert from grams into moles, or you're going to have to convert from milliliters into liters or some other volume unit into liters. So let's do a couple of more of these, and then what I'm gonna do is we'll move on to the next section, and we'll talk about the dilution. I got to get that in, and then there's one other problem that we're gonna dealing with mass percentage, and we'll be done. All right, so let's take y'all pick one of these, and let's work it and knock it out.
Can we do E?
E, perfect. Let's do E. All right. And while we're doing that, let me walk you through the other ones, right? How you would solve it. Right here, it's the same as the one above it. You got grams here and milliliters here. So you're going to have to convert both of those numbers into the required units before you can set that up. Same here. Kilograms, you got liters, you're going to have to convert this. And you'll have to do the same thing here. Convert to moles. You're going to have to convert that to liters. So once you get the conversions done, it's just putting the number, dividing the moles by the volume. So in E, it gives us, and this is a typo. Let me fix that right quick. That's the beauty of notability. Let's get rid of one of these X's. All right, so 7 times 10 to the minus 3 moles of iodine and 100 milliliters of solution. What's our problem with this? Why can't we just do this outright?
You got to convert milliliters to liters.
Got to convert. This has to be in liters. That's required. Anytime you're trying to calculate molarity, it's moles over liters, and it is never, ever any other units but moles over liters for molarity. So this needs to be converted. Right. And the way we do that is we take the 100 milliliters We multiply it by a conversion factor, 1 liter over 1,000 milliliters, right? So milliliters will cancel and we're left with 0.1 liter. We know the moles. So now it's just all academic. Put the numbers in the equation and call it a day. So we're going to say 7.0 times 10 to the minus 3 moles divided by 0.1 liters. So that's how we'll solve for that molarity. It should just move the decimal back once. So it should be 7 times 10 to the minus 2 molar. Is that right?
Yes, sir.
So it'll be 7 times 10 to the minus 2. 2 don't want to cooperate. Molar. All right. Any other questions about these? So all of these are same. So you can work through. I'm going to assign these last 3 for you to work on your own. Right, you can find the molarity of each one of those by doing the same operation. Convert any grams, milligrams, micrograms, convert that into moles. And if you don't have anytime you have grams or mass and you want to get moles, it's grams divided by molar mass. So you need to know the molar mass of HCl. In this case, you got the volume, you just run the calculation. All right, let's get into another concept with molarity, and that is dilution. Right, and a good way to think about this is you are taking a solution and diluting it or making it less concentrated by increasing the volume, right? Or taking that solution, let's say you start out with 10 mils and you dilute it up, or you add water or whatever your solvent is to get it to a different volume and decrease the concentration of the solute. So dilution decreases the concentration of, I'll zoom back out in a second. I said, I'll do it, iPad, not you. So it decreases the concentration of the solute. If you're a biology major, you're gonna at some point in either micro lab or organismic lab or 250 lab, you're gonna have to do serial dilutions. This is what you're doing. You're starting with one concentration and you keep diluting it and keep adding solvent until the concentration is different, right? And so the basic calculation here for dilution is a very simple equation. It is M1 V1 equals M2 V2, where M is the initial concentration. And then M2 is your final concentration. Right? And then V1 is your initial volume and V2 is your final volumes. What you'll find out with every dilution problem is that the concentration is always going to decrease because you're diluting it, you're making it less concentrated, and the volume normally is going to increase. So V2 is going to be higher than V1 more in most cases. All right. So let me put that over here. So I'm just going to abbreviate concentration. concentration will decrease and volume will increase. That's what happens in the dilution. You add a little bit more solvent to increase the volume, and at the same time, you're decreasing the concentration of the solute. All right. So let's look at a few of these. You can do number 9 on your own too. I'm gonna write that in here. This is the same, just like all of the ones up top. Consider this question: what's the mass of solute in 0.3 molar glucose in this volume? So you have to figure out, from, in this case, you can get moles and then convert moles into grams using the molecular weight of glucose. All right. All right, let's do number 10. Let's go number 10. So we're talking about dilution, and let me erase that. And I'll move this around before I post it. So these are all dilution problems. Actually, let me just do this because I don't want to confuse you if you're looking at the notes later. All right. All these problems will follow the same format. So let's look at A. And let me erase this back because all right. So let's look at A, number 10A. We have iron 3 nitrate solution, and it gives us the numbers that we need. We have 1 liter of solution here. 0.25 molar is the concentration, and it says it's diluted. So that means that the concentration is going to go down to a final volume of 2 liters by making the volume go up. If you take, to give a practical example of this, if you're making, again, like ramen, and you use less water, you're going to be more salty because the concentration of the solute, which is in that little packet, is going to be higher. But if the more water you use, the less salty it's going to taste because it's not going to be as concentrated. So we have 3 of our 4 numbers. We have M1, we have V1, and we have V2. All these numbers we have. So we need to solve for M2 because that's what it's asking. What is the molarity of the diluted solution? Right? So in order, and we can manipulate this right up front and apply it to each one of these examples. So M1 times V1 over V2 is going to be M2. Any one of those, if you have any 3 of those variables, you can find the 4th one just by simple manipulation of the problem, of the equation and the relationship. So now what numbers are we going to put in here? For M1, we know it's 0.250 molar. V1 is 1 liter. And then V2 is 2 liters. So liters are going to cancel. And then that's going to be basically 0.25 divided by 2, which is 0.125 molar. That's the new concentration. Any questions about that? Again, this is one of those types of problems where the only thing that can change are the units. And you can, 9 times out of 10, when you're working through a problem like this, the units are going to be given in either liters or milliliters. Anytime you see the volume in milliliters, that's an immediate signal to convert it into liters before you can do anything else. All right, so here, let's do, we're gonna, we got a minute left. I don't want to rush it. We can finish it. We're gonna finish this on Wednesday, and then we'll start chapter 4 on Wednesday also. All right, so but chapter 4 won't be on the test. The test is really literally going to be only over chapter 3. But there was so many concepts in chapter 3 that it's enough to take a test on. But we're going to stop here because I don't want to rush it. I know y'all might have other classes. So we're gonna stop right here. And if there are any questions, you can ask them now.